So what chemists have found is that by looking at a balanced equation, they came up with something called the law of mass action. That if you take your products over reactants, remember when we saw that A to B reaction, remember there were more A's than there were B's. So what we're going to do for equilibrium is we're going to say, okay, let's compare the products to the reactants. That's essentially what we're going to do. So we're going to compare products to reactants. That's what K is. K is it's called the equilibrium expression, and in general what K always does is it compares the products over reactants. Okay, and there's a reason why we want to do this. So if I take the concentration of C, I plug it in, then I take my my coefficient and I make it an exponent. I'm going to do that for each of these substances in here. We can come up with a ratio of products to reactants. So the equilibrium constant is going to be a constant, and it's not going to change because it's going to be based on the ratio. What scientists found is that when they let a reaction go to equilibrium, and every time they measure the concentration of products to reactants, they would get the same value of K for that particular reaction at a particular temperature. Now every reaction has its own value for K, and it changes with changes in temperature, but overall it was a very common number. I'll show you that in just a second. So the brackets represent concentration, as I said earlier. So we take the concentration of C to the exponential value, or we take it to the power of the coefficient. All right, so let's take a look at some data. You don't have to write this data down, but if you take a look here, this is a reaction of nitrogen dioxide converting to dinitrogen tetraoxide. So it's changing from one thing to another. Okay, so that's the chemical reaction we're looking at. That's our system we're referring to. We start out with no products, but we start with reactants. So these are 4 different experiments that are done. 4 separate experiments. None of this, all of this. Okay, so we got 0.02 of the nitrogen dioxide. So we put that in the container, it's going to react, and it's going to shift to the right. So I'm saying it's shifting to the right to produce the products. Well, at equilibrium, and that's what this portion right here is, this is when we're at equilibrium. So notice that the concentration went from 0.02 down to 0.0172. And as a result of that, the nitrogen dioxide went up from 0 to 0.0014. And when we plug that into the expression for K, which would be the concentration of the nitrogen dioxide over the concentration of the nitrogen dioxide, what we end up with is 0.211. Okay, so we end up with the value of the concentrations at 0.21. I think it might be backwards, but it's okay. So we get this value. Now they do the experiment again, but they change the amount of nitrogen dioxide. They change the amount of nitrogen dioxide. The nitrogen dioxide goes to another number, and then the dinitrogen tetroxide goes up to 0.0028. And notice when you plug that into take these numbers here, and you plug them into this equation, you get the same answer. No matter what you do with the concentrations, you always get about the same number. If you go back and put in reactants and no products, you end up with the same idea, or sorry, the opposite, products and no reactants, you get the same. So this number keeps coming up over and over and over when they apply what's known as the law of mass action, taking your products over your reactants. So K is considered, it's relatively constant. There's no units for it because we're looking at a ratio. We're comparing concentration to concentration. So therefore, since it's a ratio, there's no unit for K. Now these are what are referred to as the positions. Notice that the positions, which are the numbers that we plug into the equation, differ, but the equilibrium constant always comes out the same. So we can have any combination of these numbers that we want as long as it comes out to the same value for K. All right, and that's some general background information for equilibrium. So why would we do this? Well, because the magnitude of that number, that K, is going to tell us what's called the extent of reaction, which means how far the reaction will produce products. So if we were trying to produce, remember that reaction A to B, if we were trying to produce B, we want to make a lot of this. Well, based on that reaction, it's not going to work because we didn't get a lot of B, we had more A. So what that meant is that if I were to look at the reaction for KB, B over A, and I were to compare the concentrations of these two, well, I would have a number, K would be less than 1. Because I had more A than I did B, therefore K is going to be less than 1. What that means is I favor the reactants. I favor this, not this. So certain reactions are going to be favoring more than they will in others. So let's say we have two things. Let's say we have this red atom or red molecule reacting to form the blue one. Okay, so we got this reaction of this, A forming blue. Well, if I were to look at the equilibrium position, I let this reaction go to equilibrium, and this is what it looks like at equilibrium. Here's A, and this is how much blue that I have. Okay, so let's say that this is the scenario. Which one do I have more of? Well, I would look at K, and I would say K is equal to the products over reactants. So in this case, I would say blue over red, right? So which one do I have more of? This would be equilibrium, by the way. So let's make it equilibrium. Okay, since I have more blue than I do red, we would say that K is greater than 1. We would say that it favors producing these products. So I start with A, put it in the container, it produces B, and at equilibrium I still have a little bit of red, but mostly I have the B. Now what if it looked differently? What if the container looked like, at the end of this reaction, again, we're going to do the A going to B, and this time I have a lot more A, right? I have more of the A particles than I do the blue ones. Okay, therefore, I would go ahead and do the same thing. I would say, okay, K is equal to products over reactants. In this case, I would say that I have A would be on the bottom, and I would put B on the. This is why we always do products over reactants. So which one do I have more of? Well, I have more of the red ones this time. So therefore, this would be less than 1.0, and we would say it favors the reactants that time. All right, so that's an example of what we would call the extent of reaction. So the magnitude of K, the value of K. If K is greater than 1, we say that it favors the products than it favors the reactants. We'd say, I'm sorry, we get more products than we do reactants. We say it favors, or sometimes we say it lies to the left. Sometimes we say it lies, in this case we'd say lies to the right. Okay, in this case we would say that it lies to the left. This is just another terminology that we might use for this type of thing. Okay? All right, so that's equilibrium, equilibrium constants, and how we would express them in K. All right, so we're looking at next is what's called heterogeneous equilibria. So what we want to look at is sometimes equilibria can be what are known as homogeneous or heterogeneous. Okay, homogeneous means that everything's in the same phase. Heterogeneous means that we have different phases. So if we take a look at an example, calcium carbonate solid breaking down into calcium oxide solid and carbon dioxide gas. Well, when we look at this reaction, we can write the expression, right? We can write the K expression for this. All right. When we do that, we get the products over reactants. Now, what we want to do is we want to represent in K what's changing as the reaction goes to equilibrium, and that's the case. We want to show anything that's changing. Well, obviously the reaction is going to occur, and those are going to change, but what we have to plug in there are concentrations, right? So it's got to be that the concentration changes. Now I'm not going to go into the explanation, but I'm just going to tell you right now that solids and liquids do not change concentrations as they react. Now they will react and they will change, but their concentrations will not. They are going to stay constant. So they drop out of the reaction. Well, technically they don't. They get swallowed up by the equilibrium constant, and we just leave behind the concentration of the gas, the carbon dioxide. So here's a little rule right here. Solids and liquids do not show up in equilibrium expressions. So we do not put solids or liquids in there. We only put gases and aqueous substances. Those are the only two we put in there. Concentration of gases and substances in solution. So what you're looking for are AQ, and you're looking for gases. Otherwise, they do not show up in the equilibrium expression. Whoops. Okay. All right, so let's go ahead and take a look at some examples. All right, so let me just go ahead and do some examples for you. It's pretty straightforward, pretty simple here. All right, so I'm going to do for letter A, I'm going to write the equilibrium expression. So I'm going to put the products over reactants. So in this case, I'm going to put the concentration of H2SO4 on the top. On the bottom, I'm going to put the concentration of SO3. And I am not going to put water because it's a liquid. So what I'm looking for are only gases and aqueous. Those are the only two things that I put into those into the equilibrium expression. So this would just be H2 SO4 over SO3 concentrations. All right, so let's look at B. B, I'm going to write K equals, and I'm going to put my products over reactants. So in this case, I'm going to get rid of solids. Those don't show up. So I have just water in the gas phase, concentration over concentration of ammonia. And this time I got to watch the coefficients because I got coefficient of a 2 here, so I got to put the 2 up here, and then I got a carbon dioxide, so I get CO2. Very, very important to not forget that doubling, or them to doubling, but the concentration being squared there. All right, so for C, K equals, again I'm going to put my solid, nope, 1, no solids, no liquids. So the only thing I'm going to do for this one is I2, iodide, and I'm going to square it, iodide squared. And for the last one, I'll squeeze D in right here. All right, put D right here. K equals, I'm going to put my products over reactants. In this case, the only solid I have is the uranium dioxide. So I'm going to put H2O, brackets, square, UF4, uranium tetrafluoride to the first power, and then on the bottom, HF to the fourth power. Okay? All right, and that's your intro to equilibrium. What we'll do is we'll look at some calculations involving this equilibrium expression. But keep in mind what the value and the magnitude of K tells you. It tells you where the reaction favors. So when it gets to equilibrium, we're either going to have more products or more reactants. Not very likely we have them both. And remember that what's equal at equilibrium is the rate of the forward equals the rate of the reverse, not the concentrations. Okay? All right, guys, that's pretty much it. So we'll see you later.